In this video, we'll be taking a look at some applications of trigonometric functions that we can do up to this point in the class. So looking at what we will be doing is we'll be solving for a right triangle. And when we say solve a right triangle, it means to find every side of the triangle and every angle within the triangle. You'll see in the homework solutions that I did in this section, the very first thing whenever it said to solve a right triangle, I went ahead and did an answer setting where I listed all of the angles A, B, C, and then all of the lowercase a, b, c for their corresponding sides. So it would be very clear to anyone trying to follow along that everything is answered within the problem. Now, we'll also be solving problems within bearings. That's a direction system that we're going to be given, such as if I say we're going to travel 36 degrees west of south and how that's written in a bearing, and then work out problems based upon that. And then we'll be modeling word problems using simple harmonic motion. Okay, so first up, solving right triangles. We remember a right triangle is just an angle in which typically we denote the right angle as the angle C and the hypotenuse as side C. Thus, our legs of the triangle are side A and side B, and the acute angles within the triangle are angle A and angle B. Now, because of this being a right triangle, we know all of our SOHCAHTOA right trig triangle definitions work. We can say the sine of any angle is equal to the opposite over the hypotenuse. The cosine of any angle is equal to the adjacent side divided by the hypotenuse, and the tangent side of any angle is equal to the opposite side divided by the adjacent side. Now, when we look at that within a problem like this, where I say solve out the triangle, if I tell you that angle A down here is 62.7 degrees, and that side A is a length of 8.4. So we say, well, okay, then the easiest thing to do is go ahead and find the measure of B. You know angle C is 90 degrees, which means angle A and angle B also have to sum to 90 degrees, since the total degrees within any triangle is 180. So all I have to do is take 90 degrees minus the measure of A, which was given, and I'll get that angle B has to be 27.3 degrees. Now, in order to find out side B, I could go in and say, well, now that I know angle B up here, side B is opposite angle B, and I know the side adjacent to B, so I could say the tangent of angle B is equal to side B over side A, which is going to give me the tangent of 27.3 degrees is equal to B over 8.4. That's easy to solve for because I can just multiply 8.4 on both sides and get B is equal to 8.4 tangent of 27.3 degrees. Now in this section, your book will be consistent. They will always ask you to approximate any angle measurement to 1/10 of a degree and any side measurement to 100th of a unit. So I went ahead and just said, well, this is going to approximately be 4.34. Now, if at all possible, I would rather not use that approximated value to find another value. So you're going to notice I avoid using the Pythagorean theorem here to find the length of C. I don't want to say C is equal to the square root of 8.4 squared plus 4.3 squared. Why? It would approximately be true, but I know 4.34 is not the actual measure of side B. It's an approximation to it. So instead of using that approximation to find a further answer, I just said, well, there's no reason I would need to use it, because I can say the sine of angle A is equal to side A divided by the hypotenuse C, and I can solve for C that way. Multiply by C on both sides, you would get C times the sine of 62.7 is equal to 8.4. Thus, C is going to equal 8.4 divided by the sine of 62.7. Now, that's an exact expression for C. I know C is precisely equal to that. But again, the problem is wanting an approximation. So I approximate to 2 decimal places, and I am 100% sure C is accurate to 2 decimal places of an approximation of 9.45. Now, looking at another problem. Let's say, and these problems, the application problems in this section, they're actually shorter, because instead of solving the entire triangle, you're just solving for one measure on the triangle. If you look at this one with me, it says from a point on a level ground 80 feet from the base of the Eiffel Tower, the angle of elevation is 85.4 degrees. Using that information, we're supposed to approximate the height of the Eiffel Tower to the nearest foot. So clearly it's more easy to measure the distance on the ground than it would be to measure the vertical distance. So practically speaking, we found this measurement to be 80 degrees. And then we estimated the angle of elevation from that point 80 feet away. That angle of elevation is 85.4 degrees. Now, using that information, we can just say, well, we know the tangent of that angle should equal the opposite side divided by the adjacent side. This forms a right triangle by the very sense of how the problem is set up. So we can say, okay, no problem. Tangent of 85.4 is equal to A over 80. Notice I just called the height of the Eiffel Tower A here. So A, the height that we're looking for, is equal to 80 times the tangent of 85.4. And when we do that, we're going to get 994 feet. So we can say conclusively, and it's to the nearest foot here, that the Eiffel Tower is approximately 994 feet tall. Now, for another example here, let's say we're trying to find an angle inside of a right triangle. Okay, so it's more problematic, obviously, when you don't have either angle A or angle B. If you have one of the other angles, it becomes super easy because you just say, well, the remaining angle is 90 minus whatever angle you have. Well, what if you know it's a right triangle, but you don't know either of the two acute angles, but you do know two sides? Well, then we can use information. I can say, for example, if I wanted to solve for angle A here, I could say, well, think about what we have within this right triangle. We know the side opposite A, and we know the hypotenuse. Sine is the ratio of opposite over hypotenuse, so I can say the sine of angle A has to be 6.7 over 13.8. Now, in order to find out that, I could just say, well, I'll go to my calculator, inverse sine of 6.7 over 13.8. Please make sure you're in degree mode. And if you do, you're going to get that A is 29.0 degrees. And again, we round to a tenth of a decimal place. So we'd say, well, A is approximately 29.0 degrees with the ground. Now, if I needed to find the other angle up here, and I could easily do that. I could just say, well, it's 90 minus 29. It's going to be a 61 degree angle up there. No problemo. Now, the bearings. In navigation and survey problems, the bearings is going to be used to specify the location of one point relative to another point. So we're going to say the bearing from some original point O to some ending point P is the acute angle measured in degrees between the ray OP and the north-south line. So you're always going to give the main direction as north or south. And then you're going to give how many degrees east or west of that direction, north or south, that we're going. For example here, if I look at this right here and I say, well, here's my ray OP. How am I going to give the direction of that ray? Well, you look at it and say, well, is it going north or south? Now, what if it's just strictly on the x-axis? Well, then you would either say it's due east or due west if it has no vertical movement. But anything other than something going due east or due west, you're going to start off with the vertical mentioned first. So in this case, it's going north. So you say, all right, north. Now, we know it's going 40 degrees east of north, so you would write the bearing. And typically these bearings are read in reverse. I would read this as this bearing is 40 degrees east of north, 40 degrees east of north. Now, can you also read it north 40 degrees east? Can. I would prefer to read it as 40 degrees east of north myself. Regardless of how you read it, you write it this way every single time. Vertical movement mentioned first, whether it's going north or south, and then however many degrees east or west of that. Now on the next page, I have several of these, or actually, it's a few pages from here. So on the next page, I have one more of these. And you'll see here, if I'm trying to do the bearing, you say, well, from O to P in this case, clearly the main direction again is north. And then how many degrees east or west of that? Well, it's going west of north. It's 65 degrees west of north in this case. That would be my final answer for this bearing. Now, if I wanted to go my main direction in a southerly direction, I could say, well, all right, then I would start this bearing with the south direction. But then how many degrees east or west of south is it? Well, this one is 70 degrees east of south. I would write it as south, 70 degrees east. Personally, I would read it as 70 degrees east of south. Now, this is the page I was talking about where I have a bunch of them in here. Now, I just want to go ahead and talk about every single one of these. If I were saying, let's talk about the bearing of OA, you'd say, well, all right, the bearing OA in this case, clearly it's going north. Well, actually, do I talk? No, I don't. So I'll go ahead and talk about it even though I didn't write it over here. The bearing OA, it's going north, and then you would have to look at it and say, well, it's going 70 degrees east of north. I would write this as north and then 70 degrees east. I would read it as the ray OA is 70 degrees east of north. Now, the one I started with is the bearing OD. So you'd say, well, from O to D. How would I write that? Well, it's going south, and then we know it's going east to south. Now, unlike for A, I had to understand that there's a 70-degree angle here. It wasn't explicitly written, but we know that this is 20, so we knew that this angle had to be 70. Here, this one's explicitly written. The ray OD is 25 degrees east of south, so you would write it as south, 25 east. Now, the bearing from O to C, you'd say, well, okay, kind of like OA, it's not explicitly written. OC is also going south, but you'd say, but it's going 15 degrees west of south, and that's the way I would read it. The ray OC is going 15 degrees west of south. You write it vertical direction first, south, and then 15 degrees west. Now, the only other one I didn't do here would be B, and B is easy. You'd say the bearing OB, it's 40 degrees west of north. You would write it as north and then 40 degrees west. Now, whenever we're talking about simple harmonic motion, we're going to say an object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin D at time t is either given by the distance is equal to a times the cosine of omega t, or the distance is equal to a times the sine of omega t. All this means is that that distance is going to forever and ever go in a cyclical pattern. So it's going to have some maximum displacement, like it might go 5 units up, but then it's going to go back down, touch the original position, and then 5 units in the other direction, and then go back to the original 5 units up, go back to the original 5 units down. It's going to continue in that pattern, just like the sine and cosine functions have that sinusoidal pattern forever and ever and ever. So will this simple harmonic motion. A spring that has absolutely no resistance and keeps on going in its natural state forever and ever would have this sinusoidal motion. Now, unlike whenever we graph trigonometric functions, typically, and in this book, we always used the cosine of bx, the sine of bx. We let b equal the coefficient of x inside of our angle. Whenever we're specifically talking about harmonic motion, and it's nothing to worry about, but I just wanted to go ahead and mention it because your book uses it. The coefficient of the independent variable inside of our trig functions. Now, the variable is representing time, and its coefficient is going to be the Greek letter omega. So it's a sine of omega t, a cosine of omega t. Now, if you just want to put a b there, it's no big deal. The motion has an amplitude of the absolute value of a, so that's its maximum displacement. And it's going to go from a positive displacement of A down to a negative displacement of A, just considering about whether you're calling positive direction to the right, negative displacement to the left, perhaps, but it's going to continually oscillate between those two positions. Now the period, just like normally we would say, well, the period is always 2 pi divided by the coefficient of x. Earlier we called that 2 pi over b. Now you'll call it 2 pi over omega, but it's the exact same concept. Now, the period gives the time it takes for the motion to go through one complete cycle. So if I want to find out if my spring is initially at 5 inches beyond its natural length, and then it's going to go inward, compress, and then go back outward, the time it takes for it to get back to that original position is the period. Now, in describing the simple harmonic motion, the equation of the cosine function is used if the object is the greatest distance from the rest position at t equals 0. So think about that. It should make sense. Since the sine of 0 is 0, we're going to use the sine function to represent simple harmonic motion if the original position is at rest. It's not being stretched away in a positive or a negative direction from its natural point. It's at position 0. Well, the sine function starts at 0. Since the cosine function starts at 1, I can easily say, well, if the position is at a positive, it's going to be positive a times the cosine function. It's going to give me the displacement at time 0. Well, what if it's a negative displacement? Then I'll just multiply by a negative in the cosine function. It's going to start off negative, and then later it'll turn to a positive distance, just like the cosine function oscillates. So the easy way to do it is, if you think about it, you just say, well, if it's starting off already stretched from its original position, it's a cosine function. If it's starting off at a distance of 0, it's the sine function. Now, let's look at an example here. A ball on a spring is pulled 6 inches below its rest position. Automatically, I know I'm using a cosine. Why? Because the spring is not at rest. It's already 6 inches below its normal rest position. So I'll say, all right, that right there tells me I'm going to use a cosine. Now, that spring is 6 inches below its rest position, and then it's released. The period for the motion is 4 seconds. So we know it's going, if I release it 6 inches below and I let it go, it's going to go up, and then it's going to come back down. That entire period for it to go back down to 6 inches below is going to take 4 seconds. Write the equation for the ball's simple harmonic motion. Okay, so when the ball is released at time 0, the ball's distance from its rest position is 6 inches down. Because of that, we know d is negative. The displacement initially at time 0 is going to be -6. Okay, the greatest distance from that rest position has to occur at time 0, just like it does on the cosine function. Thus, I'm going to use the equation for the cosine function, and I know that a, the coefficient of the cosine function, is going to be -6. Now, if I'm asked the amplitude's +6. But the a value is -6. It's going to be a -6 cosine. Now, I need to find out the value for omega in the problem. And I would actually do the next page first. I would find the period first. So let me flip to it. Ooh, actually, I won't flip to it. Oh, yeah. I've done it right here. I'm sorry. Where I said I was going to find the period first. And you said, well, the period every single solitary time, it's just 2 pi divided by the coefficient of the angle. And you say, well, the coefficient of the angle is whatever omega is. So we say our period is going to be 2 pi divided by omega. We know it said it took 4 seconds for it to get back down to its original position. So the period is 4. If you set 2 pi over omega equal to 4, that gives you 2 pi equals 4 omega. And then you can divide by 4 on each side. Omega is going to equal 2 pi over 4, or pi over 2. Now, I know that that means that the omega, which is the coefficient of the angle inside my cosine function, is going to be pi over 2. I'll get pi over 2t. I know that the original displacement went down 6 units, so I have my Ball's simple harmonic equation right there. -6 cosine pi over 2t. This guarantees that when t is 0, your original position is going to be 6. It guarantees when t equals 4, your position again is going to be down at -6. And at any other time, it's going to give the position at that time t. Beautiful problem. Now, if we talk about frequency of an object in a simple harmonic motion, the frequency is just going to be that value omega divided by 2 pi, whereas the omega value obviously has to be greater than 0. And I would rather even think of it as just the frequency is 1 over the period. It's the time it takes for one period. So you say 1 cycle per period. That is our frequency. So if you say, well, your period in this problem, it took 4 seconds. So you would say, well, I know that the frequency would be 1/4 in that case. For every second, it completes 1/4 of a period. Analyzing simple harmonic motion. So the last time I gave you a scenario and I asked you for an equation. This time I want to give you an equation and ask you information about it. I actually think this direction is a little bit easier, and your homework questions are more like this. If I give you a displacement equation for your distance and I say it's equal to 12 cosine pi over 4t, the first question I'm asking here, what's the maximum displacement? You said, well, that's super easy, John, because you know that the amplitude of this cosine function is 12. It can go up 12, it can go down 12. The maximum displacement is 12 from the rest position. So that's super easy. Now, if I then ask, well, what if I want you to find the frequency? Now, here's where I would rather do the next page first and do the period. So if you're asked the frequency, I would just rather go back here and say, well, John, the frequency is just the reciprocal of the period. So how about I find the period before I find the frequency? I wish I would have put the next slide before this one. And I'll say, if I'm asked to find the frequency, I just say, it's just the reciprocal of the period. So I would rather go over here to the period, and we know the period formula is 2 pi divided by the coefficient of your angle, which in this case is omega. We know the coefficient of our angle is pi over 4. 2 pi divided by pi over 4, the pi's are going to cancel, and you get 2 divided by 1/4. That gives me 2 times 4 over 1. That's 8. So what this is telling me is that it's taking 8 seconds to complete one period. So I can say, well, all right, that is my period. Now, what's your frequency? You'd say, well, for every second, you're going to 1/8 of a cycle per second. You can say, since it cycles in 8 seconds, you're going to complete 1/8 of a cycle per second. That's going to be our frequency. And you just say, it's nothing more than the reciprocal of the period. So anytime you're asked for the frequency, I would just say, oh, find the period, take its reciprocal. And so now I've answered what the maximum displacement is 12. We've answered the period is 8 by taking 2 pi divided by pi over 4. And then the reciprocal of the period gives us the frequency, which is 1/8 of a cycle every second. And that would be it for this problem. All right, guys, please do try the homework in this section. Let me know if you have any questions. Please remember, whether you're working problems out of the book, or especially for those that's doing problems on my math lab, you'll have similar problems that I've worked out of the book to every problem that you're working on my math lab. But at any time, if you need help, let me know. Be glad to.